AP. Let's get started on our notes that are associated with Chapter 3. Alright, it's going to be a lot of stoichiometry. And stoichiometry is just a fancy word that refers to counting and accounting for things. Counting and accounting for things. So what are we going to start talking about here? Atomic masses. So you've heard of carbon-12. In 1961, it was agreed that this isotope of carbon, being carbon-12, as opposed to carbon-13 or carbon-14, would serve as the standard used to determine all other atomic masses and would be defined to have exactly, remember, infinite, sig figs, infinite number of sig figs. Remember it by if it's a definition or or a count number, has considered to have an infinite number of significant figures. So that 1, 2, the 12 wouldn't hold you back in terms of sig figs. Defined to have exactly 12 AMUs. All other atomic masses are measured relative to this. Now this might seem funny, but you have to understand that the masses of the individual atoms are so small that any normal unit for mass is not applicable. It's not useful. It's too large. And so they had to make up a unit that was small enough to measure individual atoms. So they came up with the AMU. So they had to define an AMU. Right? So they decided that carbon-12 would be defined as exactly 12 AMU. So a single AMU is essentially... go right here. 1 AMU is essentially equal to 1 proton or 1 neutron. So remember, the mass number of carbon-12 is 12. Right? That's 6 protons and 6 neutrons. Right? To make carbon-12. 6 plus 6 is 12. It's 6 protons because it's carbon. Carbon is number 6. Right? And so the way they measure the masses of these tiny, tiny things, initially, is using something called a mass spectrometer. It's a device for measuring the masses of atoms and molecules and ions, things like that. And so in general, this is a representation of a mass spectrometer. And it might seem like it has a lot going on, but I guarantee you can follow what's going on. So this is what we're going to do. So atoms and molecules are passed into a beam of high-speed electrons. Electron beam, which right here are going down. So what happens is, whatever substance you're trying to measure, atoms or molecules, whatever they are passed through this tube, and they are heated. Right? There's a heating coil to vaporize the sample. So even if they're not a gas at room temperature, even if they're typically a liquid or a solid at room temperature, which what a vapor, the term vapor is reserved for that. They will be vaporized, right? They will be heated up so they enter the gas phase. And the reason that we want to have them in the gas phase is because that they're going to have a larger amount of kinetic energy, right? A lot of energy going on, a lot of energy present in the system. So that, right, with this large amount of kinetic energy that they have, as they pass through this electron beam, which is being artificially generated, right, this electron beam, there's enough energy present in the system already, okay, in the atoms and molecules as they go through here, that when they get hit by these electrons, they become ionized, right? So this knocks electrons off of the atoms or molecules as they go in, and that transforms them into cations. Remember, cations are positively charged ions. So now, after they go through this electron beam, these are all positive things. They're all positive things. So next, we're going to apply an electric field, right? So that means we have 2 plates right here. One of them is going to be positively charged. It is going to be negatively charged. Right? They're going to be, so meaning these, this plate right here is going to be full of negatively charged particles, or sorry, positively charged particles. This plate to the right is going to be full of negatively charged particles. So realize what this is going to do to the particles as they pass through. As they enter the field, right? Remember, these are positives, right? Because they're cations. They were ionized by this electron beam. They're positives. Now, as they enter the field, and they are now right here, guess which plate they're going to be attracted to? That's right. Opposites attract. They're going to be attracted to this plate right here, full of the negatives. Zoom. And that's going to accelerate the ions. Okay, it's going to accelerate these cation this way. So as they go through this plate, they have been accelerated. This is the accelerated ion beam. And then those accelerated cations enter a magnetic field, which are emitted from these two plates. Okay. Now, the way this is oriented, I believe this is going to be negatively charged. Or sorry, a negative magnetic field, and this bottom one will be a positive magnetic field. So now that these are charged and they've been accelerated, they actually have their own magnetic field. And this causes an interaction with this magnetic field, positive up here, negative down here, such that it would curve. Since they're positively charged ions, they're going to curve upward. They're going to curve up. Why? Because they're going to curve towards this plate. Towards this plate. It's going to deflect them up in this particular case. Now, the amount of deflection is going to be proportional to the mass of the atom or molecule that went into the system. That means the most massive, meaning they have the most weight to them, are going to be deflected the least, meaning they're going to stay closer to the straight line. They're going to stay down on this plane, at least relatively. If the atom or molecule is very, very light, it will be deflected more and hit the detector plate with a greater deflection compared to this more massive ion that's depicted here on the bottom of the mass spectrometer. So once those ions hit the detector plate, the measurements are made, and you can determine the relative masses of atoms and molecules as they are deflected by the magnetic field.